This video covers weighted least squares estimation, as well as feasible GLS. One of the 6 classical linear regression assumptions is the homoscedastic assumption, which states that the variance of the unobservable error, conditional on the explanatory variables, is constant. So remember, if the homoscedastic assumption is violated, estimators can still be consistent and unbiased if the other first 4 Gauss-Markov assumptions are met. So that there's no perfect collinearity, there's linearity in the parameters, the zero conditional mean assumption, and there's random sampling. However, the estimators will be inefficient, and the confidence intervals and our typical test statistics will be incorrect. And this may lead us to draw false inferences about relationships in our data. So today we're going to look at the relationship between education and the effect that that has on how often a respondent reads the news. So we're going to do this by looking at the General Social Survey from 2006. First I'm going to pull in my data set. And we're going to start by looking at some basic descriptive statistics. So we can see that we will need to recode education quickly. You can see that this worked. So next we'll run our first simple bivariate regression. So we're going to regress news on education. We can see that education has a positive and statistically significant effect on the number of times the respondent reads the news in a week. The R-squared is about 0.058, and this tells us that about 5.8% of the variance in the number of times the respondent reads the news weekly can be explained by their education. So if we would like to begin to look at the possibility of heteroscedasticity, we can create a plot of the residuals in education. And this resulting fan shape in different directions indicates that there's probably a problem with heteroscedasticity in this model. So what people typically do in our field is when they think that there may be an issue with heteroscedasticity, they almost always use this comma robust. And this computes the white robust standard errors. Typically, when you compute robust standard errors as opposed to non-robust standard errors, robust standard errors are typically larger, and this usually drives down the t-statistic, which makes it less likely to find statistical significance at conventional levels. If we compare our two models, we see that our t-statistic is actually a little bit larger in the case of robust standard errors. So this is the opposite of what we would expect. And this tells us that there's probably an issue with model specification. So next we're going to include other factors that are likely related to education and also are probably predictive of the number of times a respondent reads the news in a week. So omitting these would lead to omitted variable bias and would create bias estimates of our coefficients. So once we include all these other variables, we can see that there's still a positive effect of education at statistically significant levels on the number of times the respondent reads the news in a week. So controlling for gender, gun ownership, and income. The effect of gender on the number of times the respondent reads the news is not statistically significant at conventional levels, controlling for education, gun ownership, and income in 2006. Owning a gun in their home seems to have this result suggests that there is a positive and statistically significant effect, controlling for education, gender, and income. And income also has a positive and statistically significant effect on the number of times the respondent reads the news in a week, controlling for education, gender, and gun ownership. The R-squared value is still fairly low, although a little bit higher than in the last model. So as we detected earlier, there's probably an issue with heteroscedasticity in this model. And so we can use a weighted least squares procedure to correct or to model this heteroscedasticity. And so weighted least squares, or GLS, assumes that the form of heteroscedasticity is actually known up to a multiplicative constant. So this is usually in cases where you have some sort of known measurement error. So in this case, the variance of u conditional on x is equal to sigma squared times h of x, where h of x is some function of the explanatory variables that's predicting this heteroscedasticity. So our corrected generalizable least squares estimates are weighted by 1 over h, which is the inverse of the variance. So in Stata, you can use a simple command, VWLS, to run a variance-weighted regression. So we'll do this, see the results. So you can interpret the coefficients in the same sort of way, but they have, of course, changed. So probably most interestingly, education is no longer statistically significant. And this is what we would expect given what we had detected earlier. So if we compare the results explicitly, you can see here statistically significant, and the coefficient was larger in terms of its substantive effect as well. And this is because in our variance-weighted least squares, we're taking into account the large spread in the effect of education on the number of times the respondent reads the news in a week, and so we diminish this by weighting it. So another approach we could use is feasible GLS, and this is in the case where the functional form of heteroscedasticity is unknown. So we have to create an estimate of h, which is our h hat. And this is the feasible GLS estimator, and sometimes also called the estimated GLS or eGLS. Another important thing to note in these models is that this r squared must be redefined to be interpreted. It is fairly meaningless in this form, so you would not interpret it the same way you would when you run a typical OLS regression. So the first step in Fgls is to run our original regression and obtain an estimate of the residuals u hat. We square that and then take the natural log. Next, we regress the log of our residuals on the other x variables, so on education, female, gun ownership, and income in 2006. And this is our auxiliary regression. Next, we obtain the fitted values, which is a g hat. And then we exponentiate our fitted values, or what we've called a g hat, to create h hat. And then the final step is the corrected form of the regression using the weights, which is 1 over h hat. So when we do this, we can see we obtained a different result than when we just ran variance weighted least squares. And that's important to note, because you can model the heteroscedasticity in different ways, and the different sorts of weights you use to help obtain your more efficient estimates will change your results. So in this case, we see that education still has a positive, but now statistically significant effect on the number of times the respondent reads the news, as opposed to the model we ran with just variance weighted least squares, where the effect of education was no longer statistically significant. So gender still does not have a statistically significant effect controlling for education, gun ownership, and income in 2006. Gun ownership still has a positive coefficient. The effect is no longer statistically significant at a 95% confidence level, although it is at a 93.8% confidence level. Income still has a significant and statistically significant and positive effect on news. So a similar thing similar procedure can be run in R. So again, I'm going to use the GSS, the General Social Survey from 2006. We're going to look at a little bit of a different model. In this case, our dependent variable is going to be education. And we're going to look at the effect of age on education, controlling for some of the other factors. So I'm going to pull in my data into R. Can run some basic descriptive statistics and our first bivariate regression model. Where we regress education on age. And age has a negative and statistically significant effect on education. So a 1-year increase in age decreases the level of education by about 0.01. So we can look at a model of the heteroscedasticity. Perhaps we think that we like to weight the variation proportional to the mean. So you can define weights in R in a not very different way than you would in Stata. So instead of the AW equals command in Stata, you just simply type weights equal and then define your weights. So now once we have added the weights to the model, see that age actually has a positive and statistically significant effect on education. So next we can run the feasible GLS using the same type of procedure we performed in Stata. So we run our basic regression and then obtain the residuals. Square the residuals. And then take the natural log of squared residuals. So an interesting difference to note between R and Stata is that the function log of x in R is actually computing the natural logarithm. So it's equivalent to ln of x in Stata. And then the function log to the base 10 of x is equivalent to the log of x function in Stata. So if you want to take the natural log in R, you use this log x function. So we compute the natural log of the squared residuals. And next we're going to run our auxiliary model. So note what happens when I try to run this auxiliary model. So we get an error. See that the variable lengths differ for age. So when you get this result, you want to play around with R and see what the issue is. So we're going to compare the lengths of these two variables. And we can see that they're different. And this is producing the error in our models. So we need to make these lengths the same. So we can do this by adding comma NAs. So basically what this is doing, it's going to pad out the missing values with NAs in this model so that there will be equivalent sizes between the residuals and then ultimately the natural log of the squared residuals and our GSS variable age. So I'm going to run this, and now I'm going to again compute the residuals, and now compare their lengths. So they're the same. So if we recompute their squares and then take the natural log, we should be able to run the auxiliary model and it works. Next, we predict our G hat. And we create our estimate of H by exponentiating G hat. And then we have our model where we've added our weights, which is 1 over our estimate of H, or H hat. Another interesting difference to note between R and Stata, R is going to dummy out these categories of income because it knows that income, or observes income, being a categorical variable, leaving out the base category. And so we can see here that age has a negative and statistically significant effect on education, controlling for gender, gun ownership, and income in 2006. Female has a positive and statistically significant effect on education. Gun ownership has no effect on education at statistically conventional levels. And various levels of income have statistically significant effects. So R is actually conveying more information to us about the effect, or the varying effect, of income on education, controlling for age, gender, and gun ownership, than we found in this data regression that we produced. So again, we can see in these different procedures how we model the heteroscedasticity really matters. So earlier in our model, where we tried to correct or account for this heteroscedasticity, we ended up returning a positive effect of education. A positive effect of age on education. And this is contrary to the results that we got in every other model. So it's important to have a theory as to the relationship between your variables, to visualize your data so you can try to model the heteroscedasticity appropriately, and to think critically about how you're going to account for heteroscedasticity in your models.